Hello students, welcome to EPG Pathshala. I am Professor P03 from Jammu. Today we are going to discuss about a module crystallographic point groups under paper crystallography and crystal growth. So students, let us see what we are going to learn in this module. The fundamental difference between the Bravais lattice and crystal structure, concept of crystallographic point groups, 7 crystal systems along with their characteristic symmetry elements. Conventional unit cells for the 14 Bravais lattices arranged according to 7 crystal systems. The 32 crystallographic point groups and their notation in Hermann, Mauguin and Schoenflies notation. Lattice and crystal structure. The concept of unit cell has already been explained. We only need to describe one cell and its contents in order to be able to define the whole crystal structure. Identical unit cells are packed together so as to fill all of space to make the whole crystal. It is important to understand the difference between a Bravais lattice or space lattice and a crystal structure. Bravais lattice is a lattice of points in space which is formed by repeating fundamental units with atoms replaced by points. There are 14 ways of arranging points in space lattices such that all the lattice points have exactly the same surroundings. These 14 point lattices are called Bravais lattices. So, a Bravais lattice is a discrete set of points in space which looks exactly identical when looked at from any of its points as when looked at from any other lattice point. A crystal structure can be built up by placing bases on each point of a Bravais lattice. A basis may be a single atom or ion, a group of atoms, or a molecule. At each lattice point, there has to be an identical arrangement and orientation of the basis. In this manner, by repeating the basis in space, in accordance with the requirements of the applicable Bravais or space lattice, the whole crystal is built up. Crystallographic point groups. By now, we are familiar with symmetry operations as applied to crystallography. A point group is a collection of symmetry operations that apply at a point in a space. These are the operations which leave one point fixed, such as rotations about an axis. Such symmetry operations may apply to a molecule, to a crystal of a particular external form, or to the region surrounding a point in a given lattice structure. In this kind of operation, translation is not involved because there is no question of movement of a point. There are 32 crystallographic point groups which consist of combinations of these elements. The 14 Bravais lattices, as would be described further in the text, are grouped into 7 crystal systems. Each of these is defined by their characteristic symmetry elements. The symmetry elements that specify the crystal systems may be put as follows. Rotation axis. If rotation about an axis through an angle 2 pi by n radians leaves the lattice unchanged, it is said to have n-fold rotation axis. N takes the values 1, 2, 3, 4 and 6. N cannot take the value 5 because five-fold rotational symmetry in a crystal is not possible. Plane of symmetry. If one half of the crystal on reflection in such a plane passing through a lattice point reproduces the other half, it is said to have plane of symmetry. Inversion center. If a lattice point about which the operation R is minus R, where R is a vector to any other lattice point, keeps the lattice identical, it is said to be an inversion center. Rotation inversion axis. It is a symmetry operation which involves rotation and inversion about an axis. If rotation about an axis by 2 pi by n radians, where n is equal to 1, 2, 3, 4 and 6, followed by inversion about a lattice point through which the rotation axis passes, maintains the lattice identical, it is said to be rotation inversion axis. There is a possibility of other symmetry operations, but they are equivalent to linear combination of the above symmetry operations. Table 3.1 provides a list of 7 crystal systems along with their characteristic symmetry elements and the characteristics of unit cell. These represent conventional unit cells for the 14 Bravais lattices arranged according to 7 crystal systems. Now we have 5 columns. The first column is on systems. The second column refers to Bravais lattice. The third column refers to notation. The other column refers to characteristic symmetry element. And the last one is the characteristics of unit cell that gives axial lengths and the axial angles. Now in the first column we show system. The triclinic system. The Bravais lattice is simple or primitive. Its notation is represented by capital P. The characteristic symmetry elements are none, and the characteristics of unit cell, that is the axial lengths and angles. The axial lengths are A is not equal to B, is not equal to C. The axial angles alpha is not equal to beta, is not equal to gamma, is not equal to 90 degrees. The next system is monoclinic system. Its Bravais lattices are 2, simple and base-centered. The simple Bravais lattice has a notation capital P, whereas the body base-centered has the notation capital C. The characteristic symmetry elements are two-fold rotation axis 1. The characteristics of unit cells and the axial lengths are A is not equal to B, is not equal to C, whereas the axial angles alpha is equal to beta, is equal to 90 degrees, but is not equal to gamma. Now the third system is orthorhombic. It has 4 Bravais lattices: simple, base-centered, body-centered and face-centered. The simple Bravais lattice is represented by the notation capital P. The base-centered has the notation capital C. The body-centered is represented by the notation capital I. The face-centered has the notation capital F. The characteristic symmetry elements are mutually perpendicular two-fold rotation axes are 3. The last column refers to characteristics of unit cell and axial lengths and angles, in which for orthorhombic system it is that A is not equal to B is not equal to C, whereas the axial angles, that's alpha, is equal to beta, is equal to gamma, is equal to 90 degrees. The fourth system is tetragonal. Its Bravais lattices are two, simple and body-centered. The simple Bravais lattice has the notation capital P, and the body-centered Bravais lattice is represented by the notation capital I. The characteristic symmetry elements of this system are four-fold rotation axis 1 and four-fold rotation inversion axis 1. Characteristics of unit cells are A is equal to B is not equal to C. The axial angles alpha is equal to beta is equal to gamma is equal to 90 degrees. The fifth system is cubic. Its Bravais lattices are three, simple, body-centered, and face-centered. Simple Bravais lattice is represented by capital P. The body-centered is represented by capital I. The face-centered cubic Bravais lattice is represented by notation F. The characteristic symmetry elements are threefold rotation axis 4. The characteristics of unit cell are A is equal to B is equal to C, and the axial angles alpha is equal to beta is equal to gamma is equal to 90 degrees. The hexagonal system which is the sixth one, has Bravais lattice 1, that is simple. It's represented by the notation P. It has six-fold rotation axis 1. Its characteristics of unit cell are A is equal to B is not equal to C, beta is equal to gamma is equal to 90 degrees, and alpha is equal to 120 degrees. The seventh crystal system falls in the system that's trigonal, or it's also called as rhombohedral. Bravais lattice is simple. Notation is R. Characteristic symmetry elements are threefold rotation axis 1. Its characteristics of unit cell are A is equal to B is equal to C, alpha is equal to beta is equal to gamma is not equal to 90 degrees. Figure 3.1a shows conventional unit cells for the 14 Bravais lattices falling under 7 crystal systems. Figure 3.1b shows the notation for angles and dimensions of unit cells as given in figure 3.1a. The various identifying features, axial angles, and lengths of these 14 Bravais lattices are shown in figure 3.1a. The notation for angles and dimensions of unit cell used in figure A is indicated in figure 3.1b. All the 14 Bravais lattices fall under 7 systems depending on the time and number of rotation axes present. Rotation symmetry is the most important in classifying crystals according to the 7 different systems. The 32 crystallographic point groups and their notations. Let us know what we mean by point group. Point group refers to a collection of symmetry operations, namely rotations, reflections, and inversions, which involve at least one fixed point of the crystal while all other points remaining invariant. Construction of a finite number of collections of symmetry elements consistent with each other lead to groups which are referred to as crystallographic point groups or simply as point groups. They are also known as crystal classes. There are 32 point groups in all. Table 3.2 provides a list of point groups and the labels used to identify them. Two notations are given here, one of which is the Hermann-Mauguin or international notation, and the other one is an older notation known as Schoenflies notation. The former is more modern form of labeling point groups and is therefore followed by most of the crystallographers. These notations may be explained as follows. In Schoenflies notation, the operations involved or the individual elements of the group are indicated. As for example, C subscript n refers to a single n-fold rotation axis. N stands for the number of elements or order of the group. Schoenflies indicates point groups corresponding to one symmetry axis by the letter C, which is followed by an appropriate numerical subscript. So, point group corresponding to a two-fold symmetry axis is denoted by capital C with a subscript 2, three-fold axis by capital C with a subscript 3, and so on and so forth. The letter C is taken from the word cyclisch, which means circular, and so implies axis of rotation. Groups capital C with a subscript Ni stands for rotation inversion axes. CNV stands for a number of symmetry related vertical mirror planes, sigma V, besides capital C with a subscript N rotation axis. Groups capital C with a subscript NH have a horizontal mirror plane, sigma H. So, the addition of mirror plane is denoted by a letter subscript next to the figure. If the plane is added normal to the symmetry axis, the letter small h is used, small h suggesting horizontal. If, however, the plane is parallel to the axis, the letter small v is used, small v suggesting vertical. The letter capital D denotes point groups containing symmetry axes only. Groups capital D with a subscript small n, capital D with a subscript small n small d, and capital D with a subscript small n small h have a number of two-fold axes perpendicular to a capital C with a subscript n axis. The subscript small d represents diagonal reflection planes which bisect the angles between the two-fold axes. The subscript small h represents horizontal mirror planes, sigma, with a subscript h. Point groups with rotoreflection axes are denoted by the letter capital S. Capital S is taken from the word spiegelachse, that is a mirror axis. As for example, 7 subscript 6 is equivalent to 6 with a wavy sign overhead is equal to 3 bar. Cubic systems are highly symmetric and their groups are represented by capital T, that is tetrahedral, or capital O, that is octahedral. The group represented by capital T has 12 rotational operations, whereas group represented by capital O has 24 rotational operations. The 32 crystallographic point groups corresponding to the type of crystal system in Hermann-Mauguin and Schoenflies notation are listed in Table 3.2. Table 3.2 shows notation of 32 point groups. The first column refers to system, the second column refers to Hermann-Mauguin notation, and the third refers to Schoenflies notation. The triclinic system has two Hermann-Mauguin notation, 1 and 1 bar, whereas the Schoenflies notation corresponding to 1 is C1 and corresponding to 1 bar is S subscript C2 within brackets capital C subscript I. Monoclinic under Hermann-Mauguin notation is represented by 2, also M, which is equal to 2 bar, and 2 by M. The corresponding to this notation, we have in the Schoenflies notation C2. For M, we represented in this notation as C subscript 1H, and 2 by M is represented as C subscript 2H. In the orthorhombic system, there are 3 notations, 2MM, 222, and MMM, which are equivalent to 2 by M, 2 by M, 2 by M. Under Schoenflies notation, it is capital C, subscript 2V, capital D, subscript 2 within brackets capital V, capital D with a subscript 2H within brackets V subscript H, bracket close. Then we have tetragonal system, which has notation under Hermann-Mauguin notation as 4. Corresponding to it, Schoenflies notation is capital C, subscript 4, then 4 bar under HM notation. Its corresponding to it is Schoenflies notation, which is capital S subscript 4, then 4 by M under HM notation. Corresponding to it in Schoenflies notation, it is capital S subscript 4H, then 4MM. Its corresponding Schoenflies notation is capital C subscript 4H, then 4 bar to M under HM notation. Its corresponding Schoenflies notation is capital D subscript 2D within brackets capital V subscript D. Then the other HM notation is 422, corresponding to 422 in HM notation. In Schoenflies notation, it is capital D subscript 4. Then the last one is 4 by MMM, which is equivalent to 4 by M, 2 by M, 2 by M. Corresponding to this in notation, the Schoenflies notation is capital D subscript 4H. Cubic system, its point groups in HM notation are 2, 3. Corresponding to Schoenflies notation, it is capital T. M03 is the next point group, which is equivalent to 2 by M, 3 bar under HM notation. Corresponding to this notation, in Schoenflies notation, it is T subscript H. The third one is 4 bar, 3M in HM notation. Its corresponding Schoenflies notation is capital T with a subscript small d. Then 432, corresponding is Schoenflies notation is capital O. The next is M3M in Hermann-Mauguin notation, which is equivalent to 4 by M, 3 bar, 2 by M. The corresponding to it in Schoenflies notation, it is O subscript H. Then is hexagonal system. The point groups of hexagonal system in HM notations are represented as 6, 6 bar, 6 by M, 6 mm, 6 bar M2, 622, 6 by mm, which is equivalent to 6 by M, 2 by M, 2 by M. Corresponding to point group 6, it is in Schoenflies notation, it is C subscript 6, C is 6 bar, its corresponding Schoenflies notation is capital C subscript 3H. 6 by M, the corresponding Schoenflies notation is C subscript 6H. Then 6 mm corresponding to it, the Schoenflies notation is capital C subscript 6V. Then 6 bar M2 corresponding to it, Schoenflies notation is capital D with a subscript 3H. Then 622, the Schoenflies notation is capital D with a subscript 6. Then 6 by mm in HM notation corresponding to it, Schoenflies notation is capital D with a subscript 6H. Then we come to the last one, that is the trigonal system or the rhombohedral system. Its point groups are represented by in HM notation as 3, 3 bar, 3M, 3 bar M, which is equivalent to 3 bar 2 by M, and 3, 2. Corresponding to it, the Schoenflies notation capital C subscript 3, capital C subscript 6, which is also equivalent to capital C 3I, then capital C 3V subscript 3V, capital D subscript 3D, capital D subscript 3. There is a practice that sometimes the two subscripts associated with various letters are written such that one is below and the other above instead of being together, as per example Schoenflies notation C subscript 3 superscript H is held equivalent to capital C with a subscript 3H and capital D subscript 3 with a superscript D is equivalent to capital D with a subscript 3D, and so on. So students, let us summarize what we have learned in this module. Number 1, the fundamental difference between the Bravais lattice and the actual crystal structure is explained. Number 2, the concept of crystallographic point groups numbering 32 is given. Number 3, 14 Bravais lattices arranged in 7 crystal systems are illustrated, described, and discussed. Number 4, the notations of point groups, both in terms of Hermann-Mauguin and Schoenflies, are explained. Thank you.